Hey, here we go. We're going to look at Unit 12. Unit 7, Quiz 12. Let's take a look at some of these problems. So on number 1 here, let me just slide some things around on my screen. Come on. There we go. All right, the graph of function f, which consists of 2 line segments and a semicircle, is pictured below. Let g of x equal x squared plus the integral from 2x, and it should be negative 2 to 2x of f of t dt. What is the value of g of t? So it's the graph of f, so I'm just going to jump right in and substitute in what I know. So they want to know g of 2. So g of 2 is equal to 2 squared plus the integral from negative 2. 2 times 2 is 4 of f of t dt. Okay, so now what I do, obviously 2 squared is 4. Now what I have to do is I have to find the area under the curve from negative 2 to 4. So that's going to be from right here all the way to right here. So let's do that. So I have a semicircle. I'm going to find that area. So this area, I'll put it as green. It's above the x-axis. It's radius 2. Pi r squared is 4 pi, but it's half of that circle. So that's just going to be 2 pi. I have a bunch of answers with 2 pi. That's good. So I've pretty much eliminated E. And now, and I'll put it in blue, the area of this triangle, because it's going to be negative. So it's going to end up being 1/2 base times height. The base is 2. The height is 1. 2 times 1 is 2. And then we cut that in half, so it's minus 1. So now the 4 from right here, minus 1 in the triangle is 3. And then the semicircle is 2 pi. So my answer here is D, 3 plus 2 pi. Okay, now with number 2, we use this same graph, and I think I put it on number 2 here. Okay, now I want to find the value of the derivative. So now we're getting into second fundamental theorem of calculus, and I'll pop over there. We're going to use that a couple times. So now, hey, this is g of x. They want to know what g prime of 2 is. So let's first take the derivative. Okay, well, g prime of x, so we just take the derivative of x squared is 2x. And now, let me bring over my second fundamental theorem of calculus. Hopefully it's showing up here. So whenever I have a function that equals the integral from a to some other function, a is a constant, and you have a function up top of f of t dt, then the derivative is just equal to, hey, leave the function. So the derivative cancels out with the integral. So it's just the derivative, actually, it's just the function. Then you leave what the upper limit of the integral is substituted into the function, multiplied by the derivative of the function. Okay, let's get rid of this. And now let's do that. So now it's going to just be plus f of 2x times the derivative of what the upper limit was, which is just 2. Okay, so let's go in and find what g prime of 2 is. So it should be 2 times 2 is 4, plus f of 2x, which is just going to be f of 2 times 2, and I probably should have put that in there. Oh, no, I hadn't done that yet. F of 4, so we're okay. F of 2x, and that'll be times 2. So what's f of 4? That's right there. That's a value of 0. So this equals 4 plus 0 times 2. 0 times 2 is 0. So my answer is 4, and I get A there. Okay, so obviously if it was any other number, you'd multiply that by 2 and combine it with the 4. All right, but that's the second fundamental theorem of calculus. Okay, let's take the third one. Same thing here. Take the derivative of a problem. We're going to use the second fundamental theorem of calculus, where I have a constant for the lower limit, and my upper limit is a function. So what does it say? When I take the derivative, and I'm first going to do g prime of x before I substitute in the 2. So it's going to be equal to 3. So we're going to put in x squared every place we see a t. And that's going to be t cubed. So we put in an x squared there, plus 1. And then the second fundamental theorem of calculus says, so there's my f of t, and I put in a g of x everywhere I see it, and then we're going to multiply by the derivative of the upper limit of the integral, 2x. Let me just call that back over here. Right, so we left the function the same. Every place in the function, we substituted in the upper limit of the interval, and then at the very end, we multiplied by the derivative of the upper limit of the interval. So it's kind of like the chain rule. And you say, well, chain rule, it was the derivative of the outer function, and it is. It's the derivative of the outer function, which has an integral there. So the derivative of the integral just cancels out, and we're left with just f. Okay, so let's now find g prime of 2. Change color here. So that's 3 times 2 squared is 4. All over x squared all to the third is x to the 6. Oh, I got to do that in my head here in a second. And then times 2 is 4. So in the numerator, 3 times 4 is 12, times 4 is 48. Ooh, I like, because I got the answer like that. And then 2 to the 6 is 4, 8, 16, 32, 64, plus 1 is 65. Okay, so our answer for number 3 is C. All right, let's keep going here. Number 4, they want to know the second derivative. Ooh, okay, so let's go through and do the same thing we just did. So I know the first derivative using the second fundamental theorem of calculus. And again, that's my function. So the nice thing is the derivative of x is just 1, so I don't really need to do that. So it's just going to be x cubed times e to the x. And I could times 1 there, but we don't need to. And now let's take the second derivative of this, and we have to use the product rule. So let's do the derivative first. It's 3x squared. Leave the second the same. Plus leave the first the same. And now take the derivative of e to the x, which is just e to the x times 1. Okay, because remember, it's e to the f of x times f prime of x. And they were nice to us and gave us 1 as a value, although sometimes that can screw you up because it might make it almost easier than you think it should be. So this is 3 times 1 squared times e to the 1 plus 1 cubed times e to the 1 times 1. So this is going to just be 3e plus 1e. And we like when this works out, when our answer comes up, that's one of the multiple choice selections. So we get 4e. Okay, so we didn't panic. Once again, we used second fundamental theorem of calculus, took the derivative. And again, notice like even on the previous problems, I took the derivative first before substituting in. Sometimes we always try to substitute the number in first. We take the first derivative, then take the second derivative, following our product rule, and then we substitute in. Okay, let's go to number 5. All right, and we want to try to set this one up. Let me just show you what we're trying to get to. We're trying to find pattern recognition. And let me scan this up here. Too far. So we are trying to undo the chain rule. And I look and I say, hey, do I have an outer function, derivative of an outer function? Is there an inner function? And is there a derivative of an inner function? And if I can find that, then that allows me to have the license to integrate, and I can go back to the chain rule. Well, let's peek at this. Okay, so now I look, hey, it looks like my cube root of x cubed minus 2. Cube root of x cubed minus 2, that is the inner function. And let me just do this right here. So when I have this inner function, x cubed minus 2. And so when I take the derivative of that, it's 3x squared. So again, if I call that my g of x, then my derivative of that is 3x squared. Well, I don't have that, but I have a 2x squared, and I can get there. Ooh, how do I get there? I can now look at this as I can multiply this by 3/2 on the inside. Whatever I do on the inside, I can undo on the outside, multiply by 2/3. I'm going to have 2/3, the integral, and up here I'm going to have my g prime of x, and then this is going to actually become, obviously it's square root, but I'm going to move it up top. So that's my f of x is something to the negative 1/2. So that's my outer function. So hopefully we see that I can, I'd have another parentheses there, because I have my inner function and I now have the derivative of the inner function, because when I multiply by 3/2, I'm going to get 3x squared, and I just had to offset that by multiplying by a constant, that I'm going to be able to, that gives me the license to integrate. And how do I do that? It is going to be 2/3. I am going to take my outer function, I'm going to raise it by 1. That's going to make this plus 1/2. I'm going to divide by 1/2. And what was my inner function? We knew that was x cubed minus 2. And so now I guess I got to do a little simplifying. Dividing by 1/2 is the same as multiplying by 2. So that's going to give me 4/3. And let's see where that comes up. Ooh, and I didn't think of my constant there. Thank you, all the answers that had the constant there. So this is going to be 4/3. 4/3 times x cubed minus 2, all to the 1/2 power. So that is going to give me, using the pattern recognition on day 59, on how to undo the chain rule.
Okay, I also have a question.
All right, so now on number 6, we're going to do u substitution, and they've kind of set it up for us, which is nice. So we have the integral of x times cube root of 2x minus 3 dx. So they say, hey, u equals 2x minus 3. So one of the things I'm going to do is I'm going to take the derivative of that. So that's du dx equals 2. And now I need to write all these, I need to write it as u equals. I need to solve this for x. So I'm going to add 3 to both sides. Equals 2x, divide by 2, divide by 2. So x equals u plus 3 over 2. That's the second thing I need. And again, that's x equals. And now I have du, if I multiply both sides by dx, du equals 2 dx. And I also know dx equals 1/2 du. Oh, I pushed the button there. Sorry about that. So let's come in and write everything down. So now this is going to be the integral of x. We just said x was, and u plus 3 over 2. I'm going to write that as 1/2 times u plus 3. The cube root of 2x minus 3 is u. And then dx, we just said that is 1/2 du. Okay, so now I've completely written everything in terms of u. I have 1/2 and 1/2. I'm going to take that constant out. I have u plus 3. And then the cube root of u is just u to the 1/3 du. And the nice thing is I can now distribute the 1/3 to everything in the parentheses. So u to the first times u to the 1/3 is u to the 4/3. And then when I do u to the 1/3 times 3, I'm going to get 3u to the 1/3, and the 1/4 out front. Hey, that's going to give me my solution right here. All right, so we didn't have to go through and actually take the integral, but just setting it up using u substitution. And the reason I had to use u substitution is because when I took the derivative of what was on my inside function, it was 2. And to get that license to integrate, I would have had to multiply by a variable. So I can't do that. So that's where I have to go to u substitution. Where on number 5, hey, when I had my innermost function, it was x cubed minus 2. When I took the derivative, 3x squared, my license to integrate already had a 2x squared. All I had to do is multiply it by 3 halves to get to my license to integrate, which would allow me to undo the pattern. So when you have to multiply by a constant, you can just do that pattern recognition. But if you ever have to multiply by a variable, we have to go through and use u substitution. Okay? All right, let's take a look at number 7. So on number 7, we want to get to the particular solution to the differential equation. So let's first find the general solution. So when we start here, I'm going to cross multiply. So I'm going to end up with y dy, and then put the dx over here, and then x squared dx. And now we're going to take the integral of both sides. And the integral of y is y squared over 2. We don't do the plus c over here. Over here, this is x cubed over 3. And now we'll add the constant of variation. Because again, if there was a constant here and a constant here, we can just write it on one side. And now we want to solve for y. So let's do a couple things here. Let's get y by itself. So I'm going to multiply everything by 2. So this will be y squared equals 2/3 x cubed. And we're still going to keep it as a constant. So again, 2 times the constant, twice the constant, but that's still just a constant. And now I'm going to take the square root of both sides. We could put a 0 in here. Let's find the constant right now. Let's let x equal 0. So that's going to make this whole thing equal 0. So hey, y squared equals c, and they told us the y was going to be -4. So -4 squared equals c equals 16. So now I have, hey, y squared equals 2/3 x squared plus 16. But I don't want to know what it is as y squared. I want to know what it is for y. So I got to take the square root. Whenever we do the square root of both sides, I have to, and I wrote it as x squared. That should be x cubed. I saw that when I looked at the answers. All right, so this is going to be y equals plus or minus the square root of 2/3 x cubed plus 16. And now I go through and I'm like, wait a second. All right, so I've eliminated E, D, and A. So the answer is going to either be B or C. And it's like, wait, I got plus or minus and they only want one of them. So now what I want to do is I want to look and say, oh, what if I put in the original point? So let's say x equals 0. 0 cubed 0 times 2/3 is 0. Plus 16, the square root of 16 is 4. I want it to be negative because it has to be -4. So once we get our particular solution, we now use that point to determine whether, especially when there's a y squared in there, whether it's positive or negative. So our answer should be B. Okay, let's go on to the free response. All right, so now compute the values of g of 4 and g of 2. So we're just going to do the area under the curve. So g of 4 is the integral from 1 to 4 of f of t dt. So I'm starting at 1, and I'm going all the way over to 4. The nice thing I notice is hey, this little 1x1 triangle is going to offset with this 1x1 triangle. So that's going to cancel out. So the only thing I have to worry about is this trapezoid. That is going to be my answer here. So 1/2 sum of the bases, that's going to be 4 plus 1 is 5 times the height, which is 1. And that's just 5/2. And so that's g of 4. So that's 1 point. And now let's do the same thing for g of -2. All right. And now, so we look at it and we're like, hey, wait, I can't go from 1 to -2 of ft dt. So what I have to do is I have to take the opposite value and switch the interval. So now it's from -2 to 1 of ft dt. And once again, it's just the area under the curve. So from -2 to 1, that's going to be this other triangle over here in green. It's obviously going to be positive. So the base was 3, the height was 4, and it's a triangle, so it's 1/2 base times height. 3 times 4 is 12, half of that is 6. But because we had to switch the interval, it's going to be negative. So g of -2 is equal to -6. Okay? Each one of those solutions is worth 1 point. All right, so let's go to part B. This is worth 2 points. So now it wants me to find the derivative, the value of the derivative at 1 and the value of the derivative at, or the second derivative. So, and I don't have that written down. Let's bring this over. Probably know what the original function is. Should be able to sneak it right here. Okay, so let's first, before I substitute in the 1, let's take the derivative. So this is going to get to the second fundamental theorem of calculus, which we talked about earlier. So the derivative of the integral cancels out, so it just becomes f of x. And we always take the derivative of the upper limit at the end, which would just be 1. So when they want to know what g prime of 1 is, that's just going to be f of 1. So let's go back to our graph. And this is the graph of f. And I probably should have labeled that here, even though it was in the problem. Okay, what is the value of the function at 1? Hey, it's 4. So f of 1 equals 4. Great. Now let's take the second derivative. So that's just taking the derivative of the derivative, which is going to be f prime of 1. F prime of x first, sorry. And then when I do the second derivative, and again, that's going to be 1 point for what I did up here for the first derivative to get the 4. And now when I take the second derivative of g, that's the first derivative of f. The reason I rewrote it was to be able to put the 1 in there. Let's go back to the graph. What is the derivative at 1? Oh, there's a corner there, so it's not differentiable. So it's undefined. Undefined because a cusp at x equals 1. Okay? All right, and so now let's go to part C. So the second derivative of g is not defined at x equals 1 and x equals 2. So we come over here, back to the graph. Hey, there's a cusp here and a cusp there. All right. So that's we just know it's not defined because f of x is the first derivative of g. So if I took the second derivative, so we'd want to find out. So it says which of these two values is or are coordinates of points of inflection of the graph of g. So what I want to do is I want to find I want to find where's my either relative max or relative min between, and let's look at these on this whole thing. So between -2 and 4, let's see if I can find a relative max or a relative min of g of x. So, well, I should know that whatever my value is as I'm going, it's all positive all the way till I get to 3. So, and let's take a look at that. So my only relative max here on G on the interval from -2 to 4 is going to be at x equals 3. Because if we look, remember, G is going to be the area under the curve, and it's all positive, so it's adding up, adding up, adding up, and then at 3, it starts being taken away, so it goes down after 3. So how do I find that value? G of 3, and let me see if I still have this saved here. But I do. So now what I would do is G of 3 is just equal to the integral from 1 to 3 of f of t dt, and now all I'm doing is come back to the graph, and I'm finding that area. So G of 3 is the area under the curve between 1 and 3, and I found between 1 and 4 before. So I know between 1 and 2 is 5 halves, and then 2 and 3, this is a 1 by 1, so that's going to be plus a half. I'm going to steal some of the work I did. So I know, hey, between 1 and 2 was 5 halves, between 2 and 3 is a half, so it's 6 halves. That's equal to 3. Okay? So, and I know they want to know, hey, where are points of inflection? That's going to be whenever my, I know my point of inflection is going to be, oh wait, am I answering? Oh, I'm skipping a problem here. Sorry. Oh wait, I'm answering, I got a different, which question does yours have? Because I have a part C, hold on, let me pause this. All right, I was just doing all the work for part C, where's the absolute maximum? And that's what I was trying to do for that. So let's come back, cut some of this, slide this over to there. All right, wondering why it wasn't matching up with the question. I have my workout. All right, so we find out the only maximum that would occur, remember, for the extreme value theorem, the maxes are going to occur either at the endpoints or wherever there's a max or min, relative max or min inside. So I just found that G of 3 is 3. And I think we did on part A, we found out what G of -2 was. We found that to be -6. And then we found G of 4 to be 5 halves. So those are the other two ones. Let's come back here. So we did, hey, we said G of -2 was -6. And we said G of 4 was 5 halves. So when I compare all three of these, 3 gives us our absolute max. All right, so we're trying to find the absolute max. The only max that's going to occur is at x equals 3. We went through and put it in, found that the G of 3 is 3. So I had to compare it to the two endpoints, -2 and 4, and obviously that one still stood the test of time. Okay, now D. Second derivative of G is not defined at x equals 1 and x equals 2. Which of these two values is or are coordinates of the point of inflection? So I know point of inflection of G, point of inflection, oh, that's not how you spell it, inflection, is when G double prime, which is when F prime changes signs. Okay, and so when does I know F prime changes signs when there's a max or a min. And we'll go back and look at the graph in a second. And I want to have either max or min. How do I know that? Well, it's when it changes from either increasing, decreasing, or decreasing, increasing. So I come here, let me get rid of all the stuff. This is the graph of f of x. So I know f of x increases all the way from 0, or excuse me, from -2 to 1, and then it decreases here. And even though it changes how it decreases, it's still decreasing. So even though f prime of x is undefined at 1, because there's a corner or a cusp, that's still going to be the maximum. Okay, so I know undefined at x equals 1, but changes from increasing to decreasing, and this is answering part D, changes from increasing to decreasing at that point. So now let's go to part D. So at x equals 1, there must be a point of inflection. Okay, and that's where, so, and again, because f goes from increasing to decreasing, that means the derivative must have a maximum. That's where a maximum is going to occur, because it's where it's 0 or undefined. In this case, it's undefined, and then that's where G will have a point of inflection. I should write that on G. Okay, that's a hard one. All right, I'm going to stop this, and then we'll let that get set up, and then we'll start 13.